Okay, hello everyone. Today, in this fourth lecture, I think it is, we'll talk about virtual planning cutting guides and do they make a difference. It will be Peter Axelsson from the Department of Hand Surgery, Sahlgrenska University Hospital that will lead this lecture. Very welcome, Peter.
Thank you, Einar. I see I said lecture 5 there, but okay. Hello, everyone. I'm happy to talk about one of my favorite subjects, and that's the 3D technique. I'm a hand surgeon working in the Department of Hand Surgery at Sahlgrenska University Hospital in Gothenburg. And before that, I was, or I still am, I hope, an orthopedic surgeon. So that's a little bit of my background. And so it will be, today will be more of a surgical perspective on things. Einar showed he had a team in Lund. I want to show I don't have a team, but I think I have some friends anyway, at least 2 colleagues here. And this is Kathleen Liebrecht, looking a little bit on guides, and this is Martin Byström in the micro lab, training on some rats there. Kathleen is a surgeon general surgeon from the beginning, and Martin is orthopedic like me. But so the orthopedic part is just a part of our everyday work. But and I just want to thank Kathleen also, because I met her when we were working in the States over 10 years ago, and at that time they had started in the Materialized to do upper extremity deformities. And she was working with Professor Stockman, who introduced that technique. So she had the Mimics program in her computer, and when she showed that to me, I just said, "Wow, I've never seen anything like it." So I was overwhelmed, and when we came back to Sweden, I started to take up this technique, and Kathleen has helped me also. I want to say I have nothing. We have no financial ties to any company or so. I've mostly worked with Materialized, but now lately also done some cases with KLS Martin. But I wouldn't say I'm totally objective, because I really like this technique. But no financial connections to any company or something. So today I'm going to talk about this process. I'm not going to talk so much about the technical part here in the beginning, the segmentation or so. I will focus more on the surgical planning and the guide design, and show some pictures from the theaters. And I'm going to mostly speak about the distal radius malunions. I have done about the majority I've done has been that it's usually a problem. You can see here on the right, when the bones heal in a bad angle. This is a wrist fracture, and it was compressed, and it has healed in this angulation here, dorsal angulation. It should be more like this, like 10 degrees volar. So we have to try to get it back to the original part. So and so there are mostly angles we're looking for, and congruence in the joints and so forth. I know Einar showed some models of the heart and so on. Of course, then it's very interesting to see how the interior, how the cavity looks like and so. But for me, as a limb surgeon, orthopedic surgeon, it's mostly the geometry and the anatomy. I want to recreate the surface anatomy and the joints. So, of course, we want to see and understand that these screws has some purchase, they get a grip in the bone, but mostly it's the exterior. So this was in the past. Here you have another fracture, and you can see there this forearm bone is a lot longer than it should be because the other bone is compressed. So we have to recreate the relation, the ratio between these two bones. And usually it's still done like this. If you're good at drawing, you make some plans, and you can measure angles and how much will it be missing when you get it to the right position. So you know about which defect you will have and how much you want to fill, and you can do the corrections in different ways, and you get kind of a different character of the reconstructed bone. And angles is not so difficult. I mean, even for me, as I can measure this and recreate, but when it comes to rotational deformities, it's a totally different ballgame. You see here, it's basically a tube, and it's very hard to see. Even on CT you can understand it, but it's hard then to recreate. So what is basically done, actually, I'm a bit embarrassed, it's still done like this. You put a plastic sheet or plastic film over the X-rays, and you draw the contours of the injured and of the healthy bone, and then you can, if you want, just to cut it with a scissor and try to make it fit. But you see, it looks almost embarrassing now, and you don't want the patient to see how you do it, because it's very, very like basic rudimentary. So this is the concept now. This is a standard radiograph, but we use the CT, of course, and segmentate it to get what we are interested in, a 3D model, and we mirror the healthy model on top of each other, and we can see how the deformity, what character it has. You can see it has almost an S shape here, and that was the reason it was very complicated. Actually, we couldn't manage it with just one cutting plane, one osteotomy here. We had to do two. And it's very compressed also, you can see here, so to get it out in length. And this is the final. It should be, you see the healthy in blue here, it's straight, and you want to get it back straight. So you get a lot more information here with the 3D on the screen. And then you have the possibility to simulate different kind of positions. So I'll come back to that. So here, if you look at this first cut, if you cut here and you move the distal bone to the desired position, you get this kind of defect in the back. But if you place the cut in a different way here, you get a total different appearance in this area. And you can also play a little bit, where will the screw catch the bone here. So what you usually do during the web meeting between the surgeon and the engineer, when you plan together, you choose where you want to have the osteotomy, where on the bone and which angles. You choose then a plate that you think will fit, and you simulate the different kind of options you have, and especially rotation, and you look in the joints, as I said, for congruency, so it fits and moves in a smooth way. So when you finalize the planning, you know how you want it to be, then you know where you want to screw. You can plan the channels or the holes for the screws, and you can make the guides so you actually get the position you want. So you make you drill the holes as you want them to be when it's finished. Otherwise, you can just put the plate here and drill the holes right away. But so because the plate is rigid, it's metal. So if you cut the bone, the bone will have to follow the plate. Here is just where you put the saw. So I want to show you. Here are the bone models. I was more excited about those in the beginning. Now I've spent more time on the computer, so now I get a better feeling for the deformity when you rotate it, and you can manipulate it in the computer. So I don't feel I need the bone models as much, but there are certain instances when they are really helpful, and I'll get back to that. You can do some extra. This is just optional. You can make when you know how the distance you have between the bones, you can make a guide for that too, so it goes quicker when you want that extra bone allograft. So you get the guides like this. When Materialize sends them now, they have some tags that you just bend away, and here you see how the guide fits on the bone. It should be really close contact, and they have some small extensions here, like a footprint or like a grip here, and the way to know where the guide will fit is to clean the bone really thoroughly, and then you draw and press and draw the guide until it almost snaps in place, because then it fits all around, and you have to check that really carefully, otherwise the planning won't work, of course. It's a little bit hard now. I don't see you, so otherwise I like when you stop me, and I can, if you have some questions, I can, but I just go on. This is chaotic pictures, but that's actually how it is in real life. There are so many different kind of plates and different kind of features, different shapes, different lengths and everything. These plates are made for fractures, distal radius fracture, because that's the most common fracture, so there's a lot of interest in this, of course. So the different materials, different shapes, that's supposed to be good. These two are kind of, or this is kind of interesting because this is a carbon fiber plate, and there are also peak plates. So when you have the possibility to X-ray during surgery with we call it C-scan fluoroscopy. So then you just, otherwise the plates are, if they are big and heavy, they will block your sight. But these carbon fiber plates, for instance, you can see. And these plates, they go very distally on the rim there. So, but otherwise, the best feature with the plates is they're kind of technically advanced. Some holes may look like this. You see the threads here, and if the screw have a thread too, it will grip in the plate. Some plates has the possibility you can lock the screw in the plate, but at an angled direction. So it's different what you want to do with the screw and the plate, different kind of features. And there are other things too, different kind of points and screw heads materializing in the plates where the screw grips. And as I said, you can angle them, or you can have small guides here for the drilling. And so they are actually quite advanced, and it's good to know how they work when you use it. I just show some pictures here from the surgical theater, and here we have opened the forearm, and you don't need this guide here. I just put it there for educational purposes. So this is what you need, and this is really nice to have. When you have opened, you put the guide down and you try to get it in the right position. So you usually have to adjust it a couple of times until you feel it really fits the bone. When you're happy with the position, you put in some steel wires with the drill. So these two are parallel, but and you slide it. You have the drill guide in place, and you lock it with those pins. So, and the next step is then to drill for the screws, and you do that through a metal sleeve here, so you don't get ruin or get a lot of plastic in the wound. And then you take away, you might take away one pin, and you have the parallel guides and the same holes in the cutting guide, so you can just slide it down. You know it will be in the exactly the right position. Then you cut the bone here. I miss some pictures here because here the plate is already attached to the bone. So you can see the gap in the bone here when we have corrected the deformity. So what you do is you put the screws in the distal part first, and then to be able to catch those holes, you have to push the plate and the distal fragment towards the hand, and then when you see the holes, you drill you put down the screws. I'm not sure I'm clear about this, but you use the rigidity of the plate, so the bone has to adjust because you have planned the holes in the bone in the how you want it finally. As I said, you can take some bone graft, and here we have the little model of the bone graft, so it goes quicker. We usually fill this gap with bone, so it heals quicker. And then you check a little bit, and you check with the X-ray, everything is okay. Is some screw too long, so it comes out in the back side or something like that. So why bother? Why all this with the CT and with the guide design? You have the web meeting. Well, definitely, and it's been shown in many papers, it's improved accuracy. You get a better, the planning is actually performs well when you see the final results. But it's hard to correlate to clinical outcome because pain and range of motion and so it can be very different in the patient. So, and we want it to be safer, of course. We want to plan, the better you plan, the less stressful or the bigger chance for success, of course. Decreased surgery time. You don't have to do X-ray all the time because you have already planned everything meticulously, and you usually, yeah, it's straightforward procedure instead of improvising and try different positions in the surgery. You have already tried the different positions in the computer. You don't have to X-ray as much. Cost efficiency is another thing. I put on when you can later, can you look at those if you're interested in upper limb surgery or so we wanted to look into a few of those questions. So I was involved in this study we published 2018 in the JBS, and what we found, this is actually the only randomized study there is. It's very hard to randomize surgical procedures actually. So, and I don't think I will do it again. I won't do it again. And what we did was we had 40 patients that we allocated to one group for standard planning, basically pen and paper, and the other group was the process I outlined before. About the surgery time, it wasn't much difference. That surprised us, but I think I have an explanation. And so that was not significant. However, we used a lot more radiation for the planning without the guides. So that was significant. these are different kind of patients' reported outcome. It includes pain and the ability to rotate your arm or lift things. But none of these were actually significant, but they were strong trends. Radiographic parameters, they were significantly improved or better, I would say, in the guided group. You can see a little bit about the dash here. It's a common functional score. So they improved a lot in the beginning, and that was okay, but the other group improved too. And that was the problem, I think, the main problem with this study, because we're quite experienced surgeons here, and to be able to collect these patients, we had to have the most simple fracture, just simple dorsal angulation, basically. And if you have done a couple of those, you don't need the guides. So it's very hard to get the difference between the groups. But that's the problem, of course, is if you want to do research in a personalized treatment. They are all very different. That's why you need the guides, because it's something something unusual with them, so it's hard to compare them. So I think that's the problem. Then the study was underpowered also. We calculated the power like 17 patients in each group in the beginning, but post hoc analysis showed that we had only 40% power. So we needed about twice as much patients to prove that there were no difference. Anyway, what's interests me, what's the difference, what's really important with this now type of 3D technique? Okay, I think it's interesting, of course, the technical process and the models and so on, because you can better understand what's going on, how the deformity looks. So there's new and additional information, but does it change anything? Yeah. And then you have the simulation and the modeling where you plan together with the engineer and the surgeon. Well, maybe Kathleen can plan herself, but I only do the surgical part, so I'm not good with this software program. So I think it's really interesting when an engineer and a surgeon sits down and really analyze things together and plan. I really like that. So this part I'm interested in, and also, as I said, the guides are really good during surgery. But does it affect the procedure? I was curious about that, so we made it a small study here. And it's just a retrospective review where what I did was that I usually have a plan before I talk to the engineer, and of course she makes a preliminary plan in the computer. So then when we talked, we looked at how we originally planned and how it turned out. Did we really change something during our session? So, and this is not published, but we looked through the different patients we had done and tried to categorize them, and we thought we found 8 different kinds of important change that we did. For 2 of the patients, I pre-bended the plate because we didn't get it to fit really good to the bone, so I had to bend it. And that I hadn't done before I started to work with the 3D planning. For 2 plates, we had to remove some bone to get the plate to fit, and we changed the osteotomy level or direction in 4 cases. The case I showed you first with the double level osteotomy, that was something new also for me, and then we did some other. For 2 cases, I saw it wasn't possible really to achieve a good anatomical position. so we didn't proceed with we just did the planning and gave up. And I'll show some examples here. Preoperative plate contouring. And so you see here the malunion. This is actually a volar malunion. It should be more like in this position here, but it's volarly angulated. So we have in blue, we have the ordinary one with the overlay here. So if we move the distal fragment to the desired position, we get this kind of appearance. So the anatomical plates, you saw a lot of different plates, but there are actually no plate that fits in a way like this. So if we use one of the common plates, it would look like this. It would be way off the bone. So what one option could be if we bury the plate in the bone. So we have to drill, or we have to make room for the plate in the bone, and that's not really optimal. But a simple solution would just be to bend the plate. You see, and that's what we did. So here you see how we bent the plate, and I'll show a little bit more pictures on how we did that later. And what we did here, the first option, if you do it traditionally, because it's really compressed this fracture, so you need to take it apart, and then there will be a big gap here. That will be a little bit problematic for the healing, but it will also be problems when you distract something this far. Usually the muscles and the tendons, or maybe not the tendons, but ligaments and so on, when this has healed in this position, they shorten, so it's very hard to get it out in the right positions. It's high tension here, and you don't have the bone cavity. So one option could be if you cut the corresponding bone here, it's the ulnar bone, the forearm bone. If you shorten that 8.5 millimeter, and you take it away a little bit here, then you have bone contact right away. You get an arm that's 8-9 millimeters shorter, but no one will notice that. But then you don't need the bone transplant, and you don't have this problem with distracting. Because this is quite an easy, you just cut away this piece and put a standard plate on top here, or a small plant. You can also choose a different kind of osteotomy. You can do it straight like this, perpendicular, or to get a smoother surface here to save the tendons on the backside. You can choose to do it differently. So you can manipulate and try. Here you had also the plate lifts a bit from the bone. And again, you have this large gap. So we shortened the other bone, and then we had some contact here, and we made a little bit of bending on the plate as well, I think. So, there should be a slide here about the results. But anyway, 15 of the 23, or was it 17? Anyway, it was more than in 50% of the cases we did a radical change in our original plans. So the planning made a lot of difference. The guide is good in the surgery, of course, but the change of surgical procedure, I think, is the planning. So, but it was not a really scientific study. We could have done it a lot better, but it was just to see a little bit like a pilot. It was not really fair because we compared the 2D to the CT. Some of the cases I would have done a CT anyway, even if I wouldn't use the 3D technique. Okay, over 50%. So and it's reasonable to believe if you get a better anatomical position, the results, the outcome should be better functionally also. It can't be bad to be normal, I think. And of course, there are some downside also. The preoperative planning takes time. So altogether, I think now if I do a fracture like this, I say maybe 30-40 minutes in the surgical theater, operating room, but I lose that maybe when I do the planning. But it's a lot more expensive to do the planning in the operating room, of course. And also, for me as a surgeon, it's a lot less stressful. I can just step by step proceed according to the plan. I don't have to improvise and so. But that can also be a problem maybe if I'm pretty sure this technique will be standard in the future. But then those surgeons won't really be trained for what happens when the plan fails, and you can be sure it will sometimes, because then you have learned to be so dependent on this planning, and there is no B alternative, no backup if something fails. That's a problem. For instance, in one of my cases, they didn't order the right plate, even if it says exactly I know which plate and the number of it. Somebody forget, and of course it's my responsibility to check that, but I checked it too late. The patient wasn't in the operating room, but we were quite far. And in the normal circumstances, I would just have changed to another plate, maybe a little bit larger or smaller or different material or something. We have a couple of plates. But now, since the surgery were planned for this exact plate, we couldn't go ahead. We had to send the patients home and get those plates, which were quite unusual. It was an unusual case. So you get very, you kind of locked to the planning. You have to be aware of that. So you have to prepare for even more. And also, as you saw those cutting and drilling guides, they force you to open a little bit more in the soft tissues. And you have to think about when you plan the guides also, so you're not in an area that is impossible to move or some structures. And also the cost, of course. You have the software program, the engineer, and so forth. Time could be a little bit of a problem also. Now, today I've only spoken about malunited fractures, and then you have a couple of months to plan and prepare. But if you're going to do fractures, which I think will be a big part of this, where you will use it a lot in the future, then it's to send to plan with a company in Europe, even if you do it over like on Zoom, but they have to send the guides and check it. I think the only way you can start doing fractures, you have the whole process in-house. You have an experienced engineer and surgeon working together and that are used with this kind of procedure. So they can, because fractures maybe, for some fractures you have 3, 4, 5 days. Some fracture can be a week. Maybe it's good to, so the bleeding will stop, but you have to be quite fast. In fact, it will be very good for fractures. You can see all the different fragments and where the screw will, how you will hook them up on the screws and so forth. This is just to show you how I did the bending, and while we're talking about the future, it's not really, this is not really the future. It's in my garage, so I can look at how the bending should be, where it should be, I can also try it on the models. And they make those small spikes here that fit in the holes in the plate. So I can bend and re-bend until I'm totally satisfied. And here you see the shape of the plate, and this is upside down. Another, usually they look like this. So it's more like S shape here. And but this is how it will be done in the future. This is a really complicated malunion we had, where we couldn't find the fitting plate, and I don't think I could have bent it either. So they 3D printed a titanium plate, and so we used it during surgery, and it looks a little bit strange here. We did him 6 months ago, and he's better than I thought, actually. So I think there will be more of this, but this is of course complicated. I'm not sure we will do that in-house for a long time. Maybe the instrument companies or so will continue to do that. This is another interesting idea. Is you do the planning and you have the contours and everything. This is for fracture. This is from last year, a paper I found interesting, and so you can do the planning in the computer as almost as we did, but then you have the X-ray machine you use during surgery. You not transform. You translate the outline, the contour there. So when you do the surgery, you know if you're in the right position or not. So you can kind of use the fluoroscopy and move the plates until it fits the contours you have planned before. This is a little bit how it looks like. So there will probably be a lot of development in this field of guiding, I think. Thank you for putting up with me, and I hope you did learn something. You were welcome to write to me if you. We do the chat, of course, and but I will. So I don't forget. I want to wish you a really nice weekend. It's Friday, and that can't be bad. So.
Thank you a lot, Peter. So we have gotten some questions during the talk, and then please have more questions. So I'll start with the first question from Hanna in Lund. So are some of the plates flexible? Or
No, not really. They are different stiffness, of course, but in this case we use the plate so we want a stiff plate because that's what's where we have the stability, and the bone will be kind of flimsy. They are basically free floating, so we attach them to the plate. But well.
So it's the plate that gives this stability, and that's what you use for getting the orientation.
Yeah.
And the difference between the plates are
it's
different.
It's more where you want the screw to purchase or grip in the bone, and it's also the shape and the length but Hannah's a little bit right, because I don't like the titanium plate so much. I think they're too rigid, and when the patient starts to when after you get them out of the cast and so on, we have had a case where the screws broke, and that was a titanium, and I think a little bit of flexibility is good. But it doesn't matter during the surgery, but it can matter afterwards when the patient starts to train and to use the hand.
I have a related question that we can take at the same time. So The difference is, as I understood it, that some plates are radiolucent, so you can see through them. That could be advantageous.
Yeah, but that's not so common. It's more like lately, the last 5 years. So
yeah, but could it be a good thing to have a mix? So one part of the plate is translucent and one is not, and then we could use it on the fluoroscopy to do the navigation. Could that be an interesting future approach?
Yeah, usually it's just a certain area you want to see. So there it could be, if it was translucent in this area, that important area. Or you can make it you can have like a peak plate or carbon plate where you put some other material in that makes it a little bit, you can see through it, but you can still see the contours, of course. So
good. So I had another question from Erik Cederberg here. So the cutting, is it not done with a kind of metal sleeve? Is there a problem with plastic getting into the patient, or is it washed away with all the bone dust?
No, the saw just cut in the distal part. So it's actually the drill. If you have the plastic, it will drill all the way down. But the saw is just the edges. Are just in the end of the saw. So when you put it through the plastic sleeve, it will go to the bone, but it's nothing, no edges that touches the plastic.
So in principle, there will be it will be improbable to get small parts of plastic unless you do.
Maybe you get a little bit, but that won't interfere or be. No, it's no problem.
Yes, and the plastic, what kind of plastic is it? And I think here also in the chat, Kathleen answered, and I think she said it's polyamide, so I think it's correct that the material uses that. It's a PA11 or PA12, I think it's called.
Yeah.
It cannot be PLA because PLA is not possible to autoclave. Because is it correct that these are all delivered to you in a sterile?
Yeah, we have to sterilize them before we use them, and that's why you can play around a little bit with them before, and then you sterilize them and use them during surgery.
Right. And then there's a question from Mien. Are the plates designed in order to be bent? Is the strength not weakened by bending the plates?
If you bend them too many times, they will be weak. But they have probably there is a little bit of weakening, but that's not clinically important if you just bend a few times. But you can't bend the titanium plates, for instance. It's the steel plates or some legering. What's that?
Okay, alloys. Yeah.
Alloys. Yeah. Yeah. So that's another reason I usually like the steel plates better.
Okay, and then so there was a question from me actually. So about fractures, how can you say something more on how planning would help? Is it for choosing the right plate, or is it for?
Yeah, the planning would help. Sometimes it's really hard to understand how you will. The fracture can be really comminuted, a lot of different fragments. So just the planning to put these fragments together so you know which fits where. I think that will be the main thing, because you have the plates you have, but then you can choose a plate that maybe, like you saw the plates I showed you that go very distal out to the rim. So if you have a fracture that is very close to the joint surface, then you need those special plates. And so I think there it's again the planning that will help the most. it might be hard to find guides that direct you or so. I don't have any experience actually to see where the real problems are. We will have to try to experiment with those, but usually the distal radius fractures, especially the intra-articular ones, they will be difficult, but they go to the orthopedic department, and most of the cases I get because I am interested in the small joint I showed you there. I did research on that, and so that's why they send those cases to me. The fractures are done elsewhere, usually. I did them before as an orthopedic surgeon, but not anymore.
Okay, thank you. So here's a question from Elena. So are there any concerns regarding biocompatibility for carbon fibers in the plates and the long-term use of carbon fiber PEEK implants?
Both those materials are quite new for those plates, and the biggest problem so far has been breakage. Either that they get loose in the screw holes, or that they just break transversely. But I haven't heard any problems with the biocompatibility. And of course, if you're afraid it will break and so on, you can remove it. And even the steel plates and so on, even if they are biocompatible, they might be a little bit in the way and irritate the tendons or something. So because there's not much room there, so you can. That's why the plate has to be small and thin, but they can't break, of course. So so sometimes you have to remove them.
But do you remove some plates after the patient complains sometimes?
Yeah. But then you check first that it's really healed. So if they have a problem from the plate, you might have to tell them, we wait a couple of months so we're sure, and then I'll promise to take it away or something.
Okay.
But this is also better avoided with the planning, of course. Then you know which areas you should avoid, where the tendons usually interfere with the plates.
Okay, a question from Camila. The pre-op images manipulations, do you do them yourself, or you help an engineer, or do you do this?
As I said, I'm interested to learn a little bit more about that, but as now we're looking into it a little bit, but I have worked mostly with Materialize, and so we do it over the web, and I don't do it. They segment and do everything. But I think it's good to have. That's why Kathleen, who has worked in the software program, she has a better knowledge of the whole process, and I think that's good for the understanding of the fractures also. So I think, if you have a unit like you have in Lund, that maybe the engineers can come up and be visitors during a surgery, assistant, and that you learn as a surgeon, learn more about the segmentation and different things, then that would be even better, of course. So, but I haven't had the possibilities really.
So both should sort of work together. I mean, what I think is the optimal, yeah.
Yeah.
Here's a question from Miane. Would it be interesting to 3D print unique plates?
Print?
To 3D print unique plates.
Yeah, like we did in the last case I showed you. You mean metal plates? Yeah, definitely. But it's more of a process that you know better than me how about to print in metals and so on. And then it's also a regulatory problem, because now the guides we use and so we don't leave anything new in the patients. All those plates we have, they are tested and approved according to the European Union regulations. But if we start to print our own plates, and if they break and so, then it can be a problem of responsibility or something. So it's both regulatory problems and technical problems, I think. But in the future, definitely.
Maybe a follow-up question. So, what would your material of choice be if printing plates? Would it be titanium, or would it be steel, or would it be PEEK?
No, yeah, I have actually much experience with the PEEK plates, but as you said, the advantage is that you can see they don't block your sight, and I think that material is quite interesting, both in terms of rigidity but titanium, I think, is a little bit frail sometimes, and then you have to make them thick. They are very stiff, but they are not so resilient when it comes to bending, and those micro bending is what wears them out, I think. Otherwise, I guess you know better than me that printing in titanium is easier, I guess. Otherwise, I like the steel, as I said. For a while I was very happy with the titanium, but now I've gone back to steel.
Okay. Here's a question from Prashant. So apart from 3D printed titanium or titanium 64, have you tried the 3D printed PEEK or carbon reinforced PEEK?
No. I would have liked to, but we have just started with the printing the plates a little bit, but it's very expensive so far, and I managed with bending a little bit myself, but instead of bending it's also a little bit, I think it's more professional. You print it, I mean, you have the planning, it should be easy. It's more like the technical and regulatory thing there. I mean, you have to have a good printer and things like that, but you can do the planning easier in the software program, I think.
If you would print PEEK plates, do you need to have this what's the jenga in English?
The threads?
Yeah, the threads.
No,
or is it holes that will be enough for 3D printed PEEK?
I think so, but it depends a little bit how much tension. I think the PEEK is a little bit weaker, so it can be a problem if you have large deformities that you have to fix the fixation, I think. So I'm not really aware of
maybe the PEEK bends.
Huh?
Maybe the PEEK bends, so in that sense there will be less forces, maybe. I don't know.
So that's something you have to try, and probably they have done a lot of testing of the PEEK plates. The different companies who there's probably a lot of literature of how it compares to the metal plates and so on, but I'm not really familiar with that. Sorry.
Here's another question from Charlotte in Gothenburg. Could you elaborate on how you make sure the guide is placed in the exact right position on top of the bone?
Yeah, that's actually what's most important during the surgery. And usually I have a small instrument because sometimes it's hard to see if it really fits the plate. So you actually have to have a very thin instrument, so you can feel around the guide. Because if you can, you shouldn't be able to put it in between the bone and the so it's just maybe 0.5 millimeter or something, you know. So visually, and you feel if it fits, it's almost sucks to the bone when you get the right positions. They are so accurate, actually. So you slide it up and down a little bit, you twist it a little bit, and suddenly you feel this is the right. And if you don't get that feeling, then you really have to use your instrument and sort of feel your way around it. Because maybe it's some soft tissue that has slipped inside, or maybe there is maybe a little bit bone or something that when you that interferes with your fitting. But so far I have felt that, because that could be a problem if the guides you make are not accurate enough. But for me it has been mostly that I haven't cleared the area enough. That's not really, that's a disadvantage also, because when you strip the bone of all the soft tissues, you interfere with the blood circulation to the bone. So it's not really physiological. That's a disadvantage. But if you're only on one side, you get away with it usually. It's nothing special with the patient, otherwise diseases. Yeah, I hope that was answering. It's a little bit hard to describe the instrument. It's like it's what the dentist has when he feels around your teeth, that if you have any holes, basically a small hook sort of looks like a hook.
Here's a question from Olle in Uppsala. Have you experimented with bending the metal plates directly on the printed patient-specific models? So compared to the printed bones?
Yeah. Yeah, I've used the models. I bend a little bit. Does it fit to the bone? Nothing. Because the plate I showed you was a little bit more difficult shape. I did it in my garage. Otherwise, if it's just a small bending you can do it in the surgery room. You have some pliers and you bend it a little bit, or you try on the plastic model, and then you bend a little bit more and until you're satisfied. So you don't always need to a workshop. You can do it on the operating table.
Right now there are no more questions what I can see. So any final questions from someone? No, and I think we're also above the time for end, so it's 1 o'clock. So thanks a lot again, Peter, for this excellent lecture. And
thank you. I'm glad you listened.
So thanks a lot, everybody.
Yeah, enjoy your weekend.